Yes, good afternoon from me too. Thank you, Mr. Hitzer, for the nice introduction. And thank all of you for coming here. I'm glad to have you as my audience. And I learned that some of you are already familiar with image processing, so I'm quite excited if I can show you something new. And for those of you who are not familiar with image processing, I will shortly explain what today's topic is about. So what is hypercomplex color image processing? Well, let's start with image processing first. I have this image of me here to show you. You can do all kinds of stuff with image data. You can sharpen it, blur it, or do other kinds of crazy stuff with it. And it has lots of applications. You might be, the young ones of you might be familiar with Instagram, for example, where you use the filter to enhance your pictures that you show to other people. This is like the most basic example, I think, for image processing. But there's also more serious applications like medical imaging, where a computer can actually help a doctor to detect the location of a brain tumor with image processing. Or another word for it is computer vision. And when you think of self-driving cars, it's beginning to become an important topic because of the car must learn how to read the road and see what happens and then process it. So yeah, all of this is image processing. Now color image processing, of course, is with color images, who would have guessed? And what is the hypercomplex part? We use special kinds of numbers. Hypercomplex numbers. This is just mean it's higher dimensional. Some of you might be familiar with complex numbers, I hope. And so it's just like a generalization of this. We'll come to this later. Okay, what are the goals of my project? Well, it was, first of all, the investigation of the quaternions. I have never worked with quaternions or image processing before, so I had to learn it when I came here. And then I was looking about applications of the quaternions in image processing, like what can you use it for, what are the benefits of it, things like this, and implement some new functions, some smaller functions, for a toolbox I work with. Actually, a toolbox by Mr. Steven Sengwein and his colleagues who wrote the book. And then I try to develop some software of my own, an image processing tool. You see this picture here? If you're far, far away, you might not notice it, but the nearer you are to the picture, the more you see these little dots. And it's like this cure, for example. Well, this is produced digitally, but things like this, some structured noise, like dots, or I show you other pictures later, can cure, for example, when you have a bad scanner, when you scan a photo and it gets distorted, but with some structured noise, not random noise, structured. For example, old photo papers. Sometimes it was, I don't know why, popular to have honeycomb structure for the paper when you print it on. And maybe if you scan this and want to get rid of this effect, you must think of, how can I do this with image processing? So that's what I wanted to do with color images, because I have not found a good algorithm on the internet who does that, so I wanted to develop this. And yes, what are the tools that we use for this? So we have to introduce, for those of you who are familiar with it, the Fourier transform. It's a very important tool in all of engineering and computer science. Then we have to introduce the quaternion number systems I have talked about. And lastly, some things like convolution filters. So we start with the Fourier transform. When I learned the Fourier transform in university, it was something like, definition, this formula, this is the Fourier transform. And mathematicians might like this approach, but if you're like computer scientist or engineer, you always think about the application more than just a formula. So I don't want to talk too much about the mathematics part right now. Just these are the formulas, okay? But what does the Fourier transform actually do? So here on the left you see some signals, actually audio signals. And when you think of a sound, or maybe the tone of some instrument or something, some tone you hear, it's always a composition of sinusoid functions like this. Like very nice waves, we can decompose the tone, the audio signal, into those sinusoid functions. That's what the signal is made of. At least that's how we model it in physics. So, but when you see only this function here, like the fat one, how do you know which frequencies, that means which kind of wavelength the sinusoids have that the signal is made of? Because you can hardly see with your eye. So you need some kind of tool that gives you these frequencies from the signal. And that is the Fourier transform. I'll give you an example for this. During the whole project I used MATLAB. It's like, for those of you who don't know MATLAB, it's like a commercial software that's very good if you want to write programs with lots of mathematics. So, in this part here is just, don't confuse it with, I'm just defining some audio signal. You see here it's like...
okay, we can't see it.
Oh. Why?
No, because the projector has a massive screen. So you have to switch such that the computer screen and the projector screen will be one-to-one identical.
This is the new. So then I'll show you this way. Okay. And so you can see that I'm just defining an audio signal that is made of 4 different sinusoid or cosine functions with different frequencies. Namely 70, 60, 150 and 111, and when we plot it, it looks like this. So, this is the first one. It looks like this. We can't actually see any of the frequencies the signal is made of. But if we apply the Fourier transform to this weird kind of signal that we can't figure out, we get very clearly the frequencies that it's made of by these peaks here. And even if we go as far as disturb the image with noise, like later here, I add just some random noise, some like normal distributed noise. It gets even harder, yeah, to see the frequencies. And of course, signals are always disturbed with noise in real applications. So you can use the Fourier transform to get rid of it. What could you actually do? You could apply like a threshold to cut off all the frequencies, let's say below 0.4 magnitude, and then you have your clear signal again. You know, if you cut off all of these, or imagine you have some kind of do a recording, and there's some device that produces a very high noise you want to get rid of, because in recording it's always, you get a headache if you listen to it with earphones or something, because it's some high frequency, and if you actually could detect the frequency that is responsive for this, you could transform this signal with the Fourier transform, cut out this frequency and transform it back, and you have your music or whatever without this high noise. Because the Fourier transform is actually its own reverse. You can just apply it twice and you have the original signal. Okay, so this is the very basic example of one-dimensional signal, but we're talking about image processing. So what does it look like with images? That's what I want to show right now. I have the image from before. And I made it smaller, fewer pixels, so my computer can deal with it. And now you can think of this image as a two-dimensional function. Yeah, right? You can plot it just like you plot an audio signal. And then it looks like this. I did too much. Just wanted this one upside. This is what I want. This is, you can interpret the image as kind of a function, you know? Two-dimensional function. And so you could apply the Fourier transform if you do it in both directions, in like the x-axis and the y-axis, and then you get a Fourier transform that looks like this. So now I took a sharpen our photo again because we don't, my computer can handle this. And at first the Fourier transform looks like this. And you might think, so, what can I do with that? There's this. You can, at first sight, there's not much information about the image. But let's try something. What can we do with this Fourier transformation? We could cut out some of the frequencies, like the higher frequencies. Higher frequencies are actually the ones that are more in the more to the left and right, and up and down. This in the middle are lower frequencies. So what happens if we would cut the higher frequencies and transform it back? Then we get the higher frequencies, of course, the details. So if we transform it back, we have like a blurred version of this photo. And I don't know if you can see it from behind. What we also obtain is some kind of small artifacts right here. It's called ringing. It's like some small waves like this when you transform it back. This is one of the things that come with the Fourier transform, where you have to be careful. And also in the software I'll show you later. When you transform something like this with the Fourier transform, it becomes this. Yeah, so this is it's not forever, but for some time you get some small waves when you transform a signal like this that has an abrupt change, like this. So you want to avoid this. When you cut out the frequencies, you want to make it like this. So you don't get the ringing. Right? You just get something more like this. So you want to avoid sharp edges before you transform it. Let me show you the difference. Can you see this? These artifacts I talk about? Maybe you can. That's it. Like these things. I want to get rid of these, and that's why you apply another kind of mask, like this one that slowly goes to zero and not abrupt. And when you transform back this one, you have a blurred image. It's actually a little more blurred than the other one, but you see you don't have these artifacts, this ringing. It's nowhere. Maybe a little bit, but it's much better than the other one because we don't have these abrupt changes. It's important for the software later. And so yeah, this is what the Fourier transform of any image could look like. But if you have this structured noise I was talking about, it may look like this. First, let me show you the picture. This is like a scan of a photo that has these honeycomb kind of photo paper and produces this strange noise when you scan it. And what does the Fourier transform of this look like? Well, now you can see. So these stars here, they are actually responsible, or let's say they're coming from this structured noise. So what we could do with the Fourier transform here is we could cut all of these stars away, and cut out all the stars, and if we transform it back, we have the image without the structured noise. Actually, here we have a little bit of ringing because I haven't done it properly in this example, but you see where we're going to. Okay. Still, we're not there. This is still a gray image. Yeah? We talked about color images. So, how can we think of a Fourier transform for color images? Well, that's where the quaternions come in. And we go back to where we left. So, first, those quaternions were discovered in the 19th century by Heimpel. And his original motivation was generalize the complex numbers, and especially looking for some geometry in it, because with complex numbers you could describe rotations in a plane, two-dimensional space, right? Something like, maybe those who are not that much into mathematics remember something like this. You have complex numbers. Maybe this is 3 plus 1i, and if you want to rotate it about 90 degrees, you can just write it like this. You can write 3 plus 1i times e to the I half. And then you get, rotated number. No, it's actually, this is -1 plus 3. So this is how complex numbers could describe rotations very easily. And Hamilton wanted to do this in a three-dimensional situation. That's why he thought about the quaternions. But the thing is, you could not just take three-dimensional numbers now. He and other people tried it for some time, but it just wouldn't work. And someday he came to the conclusion he needs 4 dimensions. So he introduced this numbers that he called quaternions for 4. And it's just basically like, if you think of a complex number that has just a real part and an imaginary part, now you have a real part and 3 imaginary parts. These are the quaternions. You have an I part, a J part, and a K part. And they are linked by this formula, right? In the complex case, you have also the I squared is -1. Now you have I squared is J squared is K squared, and IJK together. Now all of them are -1, and this is what describes the quaternion number system. So what is the basic calculus like with these numbers? If you want to add these numbers together, it's just simple, like with in the complex case, you just add the real parts with the real part, the I part with the other I part. Easy. Now the multiplication is a little bit more difficult. It's like when you multiply it, you multiply each part by each part by each part and sum it up, and you end up with this. And this is where you have to be careful, because the quaternion number system, or the algebra, is not commutative. That means x times y in general is another thing than y times x, because you have these different signs here. So it matters in which order you multiply the numbers. And we also have to take care of this when we define the Quaternion Fourier transformation later. Okay, so how can we use these numbers? They have more aspects, of course, but I don't want to show all the mathematical aspects of the quaternions and go to the question how can we use it for image processing. So we can encode color images that are encoded firstly in RGB with quaternion arrays, and we do it in this kind of way. RGB basically is just you have these three values between 0 and 255, and you get color with it that lies somewhere in this cube. So it's a three-dimensional system, and you just take these three values and code a quaternion with it, and you put these three values to the imaginary parts, not the real part. A quaternion that has no real part is called pure quaternion. This is a pure quaternion that has no real part, just imaginary parts. Well, okay. So why choose the quaternions for the color image processing? Well, let's see what we can do with it. First of all, we need to introduce convolution filters. This is something you might have heard of if you work with image processing. This matrix here represents a picture. This is a gray picture because it only has one value, right? These are like the pixels. It's between 0 and 255. 0 means black, 255 means white. And a convolution filter is when you have something like this here. It's a kernel matrix or mask, or different names. But it's essentially a matrix that is much smaller than the original picture. And what you do is you put it over the original picture, and you multiply the corresponding numbers together, like 0 times 105, minus 1 times 102, 0 times 100, and so on, and sum them up. Yeah? And the result of this multiplication and summation of all the corresponding numbers is the result we encode in the new pixel of the output matrix or the output image. So what could we do with it? Like, this doesn't look like this. I showed you this image before. Now again, the shorter version of it. If we apply a kernel mask that looks like this, just once everywhere, and then we divide it by 16 because we have 16 pixels in here. It's like divide everything by 16. Then we gain something like the average of all the pixels, right? Because it's like we just multiply them by 1, so it's basically no multiplication. We just sum them up, all the pixels of the image. We put this kernel mask on. It's 16 pixels, and then we divide it by 16, so it's the average. And that's smoothing the picture. Yeah, right? We can see it here. So this was the original picture as a function. You saw this before, and it has these sharp edges and spikes. And if we apply this convolution filter here and get the average of the of like 4 pixels that are close to each other, or 16 I mean. And the resulting picture looks like this. It's smooth, blurred, and if we print it as a function, you can clearly see how it's smooth, right? This is much nicer than this one. Of course, we lose some information, it gets blurry, but some kind of application we actually want this. So this is an easy convolution filter. What else can you do with convolution filters? One important thing, if you think of self-driving cars, they need to look into the street and see what objects are there. There's kind of they have the picture of the street, and they must identify different objects. So you must take the picture and separate the regions. And to separate the regions in the picture, like the street or the building, you have to know the edges. How could you detect the edges? You could take something like filter like this, maybe, if you're in a three-dimensional case. Not three-dimensional case, in 3x3 matrix, I mean. So what does this kernel mask do to the picture? If you have, for example, let's say this is a picture, and I just we have just one big edge somewhere, like here. This part is all white. Okay. This is all white. This is all black. So we have zeros in here. This is our picture, and so on and so on. And here we have, well, in the normal case it's 255. Let's just for easy. Let's say now there's our ones. Ones mean white. 0 means black. What happens when you apply the kernel mask to this? Well, if you apply it here, these are all ones, right? So you have, if you go and take this one, right? Apply this one there, this one there, this one there, and so on. You get -1, -1, -1. You get 0, 0, 0. You get 1, 1, 1. So the result is 0, right? But if we, and it's everywhere until here. So no matter where we put it in this region, it's always 0. But if we put it here, actually we have -1, -1, -1, 0, 0, 0, and 1 times 0, 0, 0, 0. So we have -3. So we have something different than 0. And if we take, for example, the absolute value of it, we have a high value in the regions where we have the edge, and close to 0 in the regions where we have no edges. Right? And you could do this to a three-dimensional picture like this. This is something, it's a little bit more complicated, but it's basically this idea. You have a picture and you get the edges of it, but you could also do this with quaternions, like this. And this is a new kind of edge filter that was introduced by Mr. Sengwein, from this book. Because it not only gives the information about where are the edges, but it also preserves some information about the color. Yeah. So I must hurry up. But you can Hamilton introduced the quaternions to describe rotations, right? These are a very easy formula to describe a rotation. If you have the let's say P is like a three-dimensional vector, you encode it as a Q quaternion. And if you have a rotation axis you want to rotate it about, you can just write, if Q is the rotation axis, Q times P times Q conjugated, and then you get a rotation about this axis Q. And this is what we will use here. We will use something like this that's called biconvolution because you do it from both sides. That's basically still the same. And you see over here, we just take the value, and down here, like in the one part, we rotate the value. So what happens? If we have like the same number, or at the same color, we have, for example, red like this, and on the top it's still red, but on the bottom we rotate it on 180 degrees to green, and then we sum it up. And sum up means we get the middle of it. We sum it up. There's some coefficient before this, like I think it's 1/6, so it's the average, not just the sum. But we end up in the middle of it, and it gets gray tone. But it's like opposite colors. Like if we have an edge with red and green, like horizontal edge where we have red on the top and green on the bottom, and the red stays the same because here are ones, and we rotate the green pixel with this rotation below. We get 2 times the red, and the average of this is still red, right? So if it's a color edge, then we receive a color, and if it's not a color edge, if it's just smooth, then we receive a gray picture, and it looks like this. So this is the original picture, and if you look closely, I hope you can see it. There were the horizontal, only the horizontal, because this is not a full filter, but only horizontal edge. You can see some color, right? And if we subtract the gray part of it, and we can just see the edges right there. And they preserve some color information, right? We go from blue to red, then the color is blue. We go from red to blue, then the color is red. So this, in some cases, might be convenient. Okay, and there's some more things the quaternions can do. Unfortunately, I don't have the time right now to show you. I just show you quick with the code. We can decompose a picture using quaternions in different color aspects of the picture. Like if we say we want just the red part, everything that's red, we can use something that's called the orthogonal plane split that quaternions have. We can split it in a red part and in a part with all the other colors. Yeah, right? This is green, this is not red at all, it's just a piece here. And so we can separate, and if we only want to work on green, for example, we don't have to disturb the red part of the image. We just take the green part, change it, and then put it back together. If we look at the Fourier transforms of these, it's interesting, because this one is the Fourier transform of the full picture, right? And this one are the Fourier transforms of just the red part to the left, and the Fourier transform of the green and blue part to the right. It's like the red part to the right and the green part to the left. And this is much more. You can distinguish it much more clearly with this. Okay, and finally, we have the Quaternion Fourier transform, and this is why essentially we encode color pictures with quaternions because we can define a Fourier transform for it. This is the basic formula we have seen before, right? And it's quite similar. We have this function term here in between two of these exponentials. And right here, this f and g are some x's for this orthogonal plane split. It's like for this orthogonal plane split, you need some vectors that define the plane. This is f and q, and then you can split it with this plane and an orthogonal plane. And so, if you define the Quaternion Fourier transform like this way, it has the benefit that these you can transform these orthogonal planes separately. There are many different ways how to define a Quaternion Fourier transform. Like I already know like 8 or 9. So there are many ways, and they all have some slightly different properties, but all of them make sense. And that's what I want to show you in the last part. What I did, the software tool, the image processing tool I developed, I showed you this image earlier, right? With the, I just have to wait until the program is fully calculated. Okay, we have this image, and we want to get rid of this structural noise wherever it comes from. And we could just simply apply a blur filter, of course, like if we could show this one. We could, of course, apply a blur filter to get rid of the structural noise, but we lose sharpness, and we want to preserve the sharpness. So this is not the best option for it. And if we look at the frequency spectrum, if we transform it with the Fourier transform, we see, again, like with the great picture, all these little peaks. And I programmed the software that detects these peaks like this. Actually, what I did is I took a blurred version of this one, like that is so blurred that you can't see peaks anymore, and compare this image with this blurred version and divide them each other. And so if it's, I divide the blurred version to this, and if it's a very low value, that means we have a peak. And that's how I detect the peaks. And we have to cut the middle one out, because this is essentially image information that we can't sacrifice. That's why I cut the middle one out. Again, if we cut things out, not like this, otherwise we get ringing. And some parts of the image I replace with the blurred version of it. This is like the Fourier transform of the blurred version. So I cut these peaks in the frequency domain out and replace them by the frequency domain of the transformed blurred image. So, and like this, we won't get completely rid of these small circles, if you look here, but we preserve almost all of the sharpness. And if we want to get completely rid of the circles, we could always apply like a small blur filter to it to get completely rid of it, but it's still much more sharper than just applying a Gauss filter. And this works for all kinds of images, like this is another one, where like this is basically a scan of an image, like you can find a newspaper. It's very cheaply printed. So sometimes when you have a cheaply print a picture in a cheap scanner, it gets like this, and you can, the software also calculates all this noise pattern. Okay, now I have to stop, and yeah, I'm sure I hope I could have shown you something new, and thank all of you for your attention, and thanks for coming, and we can all
Thank you very much for the very interesting presentation, showing all what you learned and the own ideas you put into the algorithm, into working on a picture. So we have just about 5 minutes time for questions. So any question is welcome, be it very fundamental or applied or theoretical.
I have a very simple question. I didn't just get it when you use the Quaternion Fourier transform for denoising the image with the circles. In the Fourier transform formula, there are some parameters like axis, right?
I'm sorry, Larsen?
In the Fourier transform, you said Quaternion Fourier transform can be defined by several ways, and you introduce some parameters into that.
Yes.
How did you determine those parameters, the directions?
It's like this one I have here. This is just a very, very basic Fourier transform, and this is just, if you the transformed image is also 4-dimensional. So this shown here is just the magnitude of the magnitude of the vectors. We could use another kind. You talk of these parameters, right? Those F and G. Actually, this one, this Fourier transform is another, but I wanted to show you this one too. We could actually. If you look at, now I use this one here that is suitable for this orthogonal plane split, and I split the image like I showed before with to have the red part and everything else. Now I split it into a gray part and color part. And if you see
luminance
the luminance prominence, yeah, this is just this is the color part, Fourier transformed with this kind of one, and F and G are the quaternions that corresponds to the choice of plane that I want to decompose it with. This is the color part, and this is the gray part. Yeah, so you see the gray part is actually way more distorted than the color part. So if you transform it separately using these planes, you don't have to cut out as much in the color part. So you can preserve some sharpness for the colors, and just apply the regular cut to the gray part. So you preserve some information, color, and so like to determine these parameters, the gray axis is just, if you look at the color group, the gray axis is just the direction 1, 1, 1. So this is your axis, and
F equals G in this case.
Yeah,
so
and
just use one axis F equals G.
Yeah, in this case you can, for this decomposition, you can say G is like minus F, right? I think. Not completely sure, but like G is F or minus F. Yeah, and then you can decompose it like that.
In case of a color image, we have 3 channels.
Yes.
But in some sensors, for example, satellite images have more than 3 layers or channels in one image. Your method can be extended to that.
Yes.
Using Quaternion,
some animals have more than 3 color receptors, and they can also stuff like this. Yeah. There are the next generalization is the octonions, right?
Yeah.
I'm not sure if there's a Fourier transform up there.
It is possible, but it's not so easy.
Okay. So yeah, you can generalize it. Yeah.
I mean, otherwise you could also use Clifford algebras, which are still associative and go to higher dimensions.
In theoretically, but in computation, difficult.
Yeah, like the green book there shows how to optimize the computation with high-dimensional Clifford algebras, and there are now a variety of people working with different approaches. For example, they compute Clifford products with help of a tree, which only computes the non-zero results of blade base product and omits on the other. And because the multiplication table of these algebras is very high-dimensional, for the really high-dimensional computations, they don't pre-compute the multiplication table. They compute it basically on the fly when you need the product. Let's thank the speaker again.